So you see, it's linear algebra still. After all those years, I'm still learning, and well, that's my favorite matrix. I don't know if it's, recognize that matrix up there. It's the one on my website with cupcakes that my class made for my birthday, I think. If you look closely at the cupcakes on that website, you see the 2's down the diagonal and the -1's. But today I'm thinking of it as a tridiagonal matrix. So I'm thinking that a lot of today's discussion will be about banded matrices, and tridiagonal being the simplest and most important. And may I start with a fact about the inverse of tridiagonal matrices that I was not aware of for a long time, only until recently. And can you see that's a typical 2x2 submatrix of the inverse, and you see, of course, that its determinant is 0. And that's a fact about the inverses of tridiagonal matrices. This type of matrix is often now called semi-separable. There are books written about that class of matrices, and before that about tridiagonal matrices. Can I start by remembering how do we prove that, well, I think there would be different proofs of this fact, that in the inverse of a tridiagonal matrix, you have this sort of rank 1 above the diagonal. You see every row is a multiple of other rows, and columns below the diagonal. So why is that true? Well, the neatest proof, so this would be the only proof in the lecture, uses another fact that is not very well known, but it's quite beautiful. So the word nullity means the dimension of the null space, the number of independent solutions to AU equals 0, or if A is the matrix. And then the theorem connects a lot of matrix theorems are well expressed by thinking about 2x2 block matrices, not necessarily square. And so here's the matrix. A is the matrix ABCD, and then its inverse has complementary blocks, right? I'm thinking of the blocks PQRS as they have to be the right sizes to multiply the ABCD matrix, so that's fine. The J and K is just getting the sizes right. But then the remarkable fact is that the nullity of A, that's the number of solutions to AU equals 0, equals the nullity of S down here in the inverse. Well, in the 2x2 case, that would just mean that A is 0, that position is 0 when that position is 0. Of course, completely clear for 2x2. But it's a neat fact for invertible square matrices of all sizes. So I'd like to show how that theorem leads to this fact about the inverse of tridiagonal matrices. So can I just practice? So I'm practicing using this theorem. I don't very often include a proof. Actually, I don't include a proof in my class very much, which is probably bad. I don't know if you've seen the linear algebra websites. the MIT OpenCourseware. But if you look closely, other faculty criticize. They say, where are the proofs? Where are the theorems? I say, in the book. But not in class. However, today's an important day, so you get one proof. So there's the matrix A, and you can see the submatrix, the all zeros submatrix that I'm paying attention to. So that all zeros submatrix, of course it's all zeros because A is tridiagonal. And now I want to find out something about the corresponding matrix in A inverse. I want to find, this is what I want to conclude, that it has rank 1. So what's the thinking there? So look at the first, the top matrix, that 0 matrix, so that's completely null matrix. So it's in row 1. Yeah, that's just row 1, that 0 matrix to start with. It's in row 1, and then I think the first column, right, if it's tridiagonal, the diagonal entry would come first, and then the up the one above, and then we get all zeros. So do you see that that 0 matrix uses columns 3 to n? It has, in other words, it has n minus 2 columns, because the first 2 columns are not 0. So and it's completely null, so it has n minus 2 independent solutions because it's a 0 matrix. So its nullity is n minus 2. And then, therefore, by the great nullity theorem, the block in the inverse also has nullity n minus 2. Oh, I see what's coming here. The big fact, the counting theorem of linear algebra, if I have a matrix of rank R and it has n columns, then what do we know about rank? What's the nullity? So imagine a matrix with n columns, and its rank is R, so it has R independent columns. And then how many solutions to AU equals 0? N minus R. That's the key counting theorem. The number of equations that are really there, R, subtracted from the number of unknowns gives the number of solutions. Yeah, those two quantities, the rank and the nullity, add to n. Okay, so, and then that matrix that I'm pointing at, I guess I could do this electronically. Yes, there it is. So that, by the previous slide, we remember the rule is if this used columns 3 to n, then this one uses rows 1 and 2. If this one used, okay, if this one used row 1, then this one uses columns 2 to n. That's the complementary part. The rows of one are complementary to the columns of the other. Anyway, it's in the right position. It's got n minus 2 columns. And its nullity has to be the same. No, it has n minus, how many columns is it? From 2 to n would be n minus 1 columns. It's only missing column 1, this guy. So it's missing column 1. So it's columns 2 to n. So it has n minus 1 columns. And its nullity has to agree with the nullity up there. So that leaves, finally, a rank of 1. Okay, I'm sorry this is probably not I had to ask you to keep that theorem in mind from the previous slide and use it here. Anyway, it gives a very clean proof of this rank 1. And here down below, it's the same thing. If I have 2 rows of zeros, I learn something about this, but again, what I learn is rank 1. Okay. So that was, the point of that was to show this remarkable property of the rank 1 off the diagonal, this semi-separable thing. Okay. Now, okay. So now, okay, that's one point in the talk. The end of that point, the semi-separable rank 1 thing. Now, coming next is a problem of completion. A lot of interest in completing a matrix like that matrix B, where you're given part of the matrix, but some other part is not known. One important example would be, so it's the matrix that you might use in computations. Say if you were doing least squares, weighted least squares, you would want the covariance matrix that tells you the correlation between. So imagine this matrix tells us the correlation between, that's the variance, the correlation of the first unknown with itself, and then maybe 2 is the covariance, the correlation, or covariance better, of unknown 1 versus unknown 2, but we don't know 1 and 3. We don't know the correlation there. So what number do we use? That's the completion question. What's the right number to put in there? When we, in a big problem, if we were estimating maybe the height of the ocean, well, we have a lot of noise in the measurements and a lot of correlation. The error at one part of the ocean would be closely correlated with the next observations. But you might have 1 million observations, 1 million by 1 million matrix, and a covariance, you couldn't compute or work with the exact covariance matrix, and you would have no way to get it. So you must do some computation on the diagonal of nearby points next to each other, and then you must complete the matrix. So that's one application of completing a matrix. And at the beginning, everybody just completed by zeros. The simplest way to do it, if you don't know what that number should be, call it 0. The most important number in mathematics, right? It's the right-hand side of all our equations, is 0. So, but that's not a good choice. And it turns out that the good choice is the one, or maybe I should say a good choice, is the number that makes the determinant a maximum. Interesting that the determinant plays a big part here. Because for so much of numerical linear algebra, I think Cleve Moeller was the previous Charlemagne lecture. Well, he would say, never take the determinant in your life. But here, the determinant, maybe you remember, the determinant comes in, it's connected to the entropy in a Gaussian distribution. Do you remember if you have a multivariable Gaussian, you have that exponential with the covariance matrix up there, and then you divide by square root of the determinant, and that number, that determinant is important. So here's the nice result. What's the best x? What x makes that determinant a maximum? And this is not my own work, let me emphasize. This is earlier, and I'll mention some of the mathematicians involved. It turns out that x equal 1 is the best x. And in a way, this is the simplest way to see the reason. If we want to let me just point to it. If I want to maximize the determinant, then I should take its derivative with respect to x to be 0. But we remember that the determinant, that cofactor expansion for the determinant has, that x would multiply its cofactor, and it would show up in the derivative. And so the answer is the cofactor should be 0. A cofactor being the, you remember what the cofactor is? The cofactor is the determinant of the remaining two rows and columns. So let me say it again. The cofactor of this x is this 2 by 2 determinant. And when I just use ordinary calculus and say the derivative of the determinant should be 0, then it's saying that cofactor should be 0. So that's exactly what we saw. It means, so what are the steps here? This is important. Start with this tridiagonal start. Complete the matrix with the best x, and the best x is the one that makes those have rank 1. So that number should be a 1, so that 2 times 4 equals 8 times 1. And therefore, so what do we now know? We know that after completion, the inverse is tridiagonal again. That's great, attractive. Start with a tridiagonal matrix. Complete it in the best way. Maximum determinant. Then the inverse of the completed matrix is tridiagonal again. Maybe it's on the next page. Well, here's another way to see why x equal 1 is the good answer. Did you know this? There's so many things in linear algebra that are wonderful. And, well, Jacobi would have known, he knew everything about determinants, but now we don't see these facts very much, but for this 3 by 3 determinant, isn't that good? That 2 by 2 determinant times this 2 by 2 determinant minus that corner and that corner. So we can see that if we want this to be a maximum, the best choice is make this 0, because I'm subtracting a square. So since I'm subtracting a square, the best one to choose is make that determinant 0, and of course that's achieved by x equal 1. So that's another way to see the x equal 1 is the right choice to maximize the determinant. And then we've completed it. Okay, now, there are these various steps here. Recognizing determinant of tridiagonal, step 1. Completing tridiagonal, step 2. Recognizing that when you complete it, the inverse is back to tridiagonal again. So here's our example. There's the matrix, there's the 1 which is completed. Now I've inverted it, and I'm back to tridiagonal. So you see that we started with a tridiagonal matrix, and we ended with a tridiagonal matrix. It's a nice transform between tridiagonal to tridiagonal. By completing and inverting. So take a tridiagonal, complete it, invert it, it's tridiagonal again. So there, and happily, in the computations I was speaking about, like finite elements, the weighting matrix, the covariance matrix is the inverse. It's the inverse covariance matrix. So it's just this tridiagonal matrix that comes into the computations. It's a very neat little part of linear algebra. A little bit different. Probably, certainly was new to me. And then finally comes the last question. Since we, on this topic, the last question is, we started with a tridiagonal and we ended with a tridiagonal. And then do we have to take that intermediate step of completion and inversion, or could we go directly from the original tridiagonal, which was just these three diagonals, to these three without the completion step? And the answer, you see, is yes. So this is let me say, the next slide will show the formula that takes the tridiagonal, doesn't take the completion step, and I'm showing you 3 by 3, but of course these matrices are, in reality, are much larger. And I want to show you how to get the inverse, how to get that C inverse without the B, without completing B. So I started with A, ended with his C inverse, and is there a direct route, a direct path? And there is. So this is what I want to say here. I'll show you the formula, and I was hoping to find, it's so surprising to me, but I have not found a really good application. So I'm looking for applications of this formula. So here comes. So that's the line to look at up there. So the formula says, to find this inverse guy, which we found after several steps, the direct path is invert the 2 by 2. Let me go back and put it up here. So here's the formula. Take the 2 by 2 submatrix there, invert it. Take the other 2 by 2 submatrix there, invert it. So those fit into the inverse matrix. And then you have to subtract the overlap, which is just the 1 by 1 matrix 8. So that's what you'll see. To find this matrix, C inverse, to find C inverse, I claim that you could invert that 2 by 2, invert this 2 by 2, add those together, put those together, then subtract the inverse of the overlap, which is just 1/8, is subtracted from the diagonal, and there it is. So that's the 2 by 2 upper inverse, the 2 by 2 lower inverse, and subtracting the overlap, and you get the correct answer. And then to prove that to see the algebra behind it, you can do the same with symbols. So again, we start with this tridiagonal. We would complete it. Oh, well, actually, block tridiagonal works too. That's important to say for applications. These can be block tridiagonal. Then that would be the correct completion. The inverse of the completed matrix can be found without this by inverting that one, inverting this one, and subtracting the inverse of that block. So I would be very happy if you can see a use for this formula or even the history of the formula. I met it in in papers by Charles Johnson, and then in Oxford last summer, I saw some statistics literature, older, 20 years before the math literature, that seemed to have this amazing inverse, local inverse, I would call it, because each of those steps there is a local. It's a local 2 by 2, 2 by 2. And if we had a bigger matrix, of course, we would have many 2 by 2s, subtracting many 1 by 1s. And It is in the statistics literature. Yeah. 20 years before it found its way into mathematics. Yeah. Okay, so that's one collection of topics that I wanted to present, because I just think those are cool results. Now I think, I have to admit that that theory is for banded matrices, that it's for problems really that come from one-dimensional PDEs, for example, one-dimensional objects. The two-dimensional Laplacian, if we start with a square grid or a grid in 2D, then the matrix, the Laplacian matrix for 2D it doesn't have a property called chordal, and the formula is not correct. Right. So it's limited to banded matrices. Okay. Oh, what's this? This is something entirely different. It's kind of cute, I think. This was a year ago. Email came from somebody I didn't know in England, in the UK. And here was the email. So he had, I took a random 2x2 there. Pretty random 2x2, and squared it, and got that answer. And then the observation by this Peter Larkham was that the ratio 10 to 15, this ratio off the diagonal, was the same as the original, 2 to 3. Okay. So then fortunately, he tried the cube, A cubed. So he multiplied this matrix A by A squared and got A cubed. And he looked off the diagonal of A cubed, 54 to 81, again 2/3. So I don't know if that's a proof, but it does not, you think, oh, it can't be an accident. It must be right. And so then Peter Larkham's email said that this is always true. And let me say, I wouldn't, you might like to think of a proof or work out a proof, because as he stated it, it's a theorem about 2x2 matrices. So how bad can it be to see that, and it's just a crazy, but crazy interesting observation. Why should this take any 2x2 matrix, essentially any, yeah? If it had zeros there, we would have to make some convention. So say non-zeros. Take its powers, and you will see that the ratio off the diagonal is the same for all powers. So it's a nice observation. And then it's natural to ask, what about bigger matrices, bigger than 2x2? It doesn't work for 3x3 matrices unless they are tridiagonal. It turns out tridiagonal is perfect. The tridiagonal is such a cool property of matrices. So it wasn't any serious difficulty to extend this result to tridiagonal matrices. If anybody has seen such a fact before today, I would be happy to know, because to me and to everybody I've asked, it was news. That ratio B over C was the same for all powers for the inverse, for functions of the matrix. It's just a nice thing. Well, if you demand, I'll give a proof. Well, I don't hear a big demand, but and let me repeat, I don't prove that much, but here you think, okay, that's a small but striking bit of information about off diagonals. So again, I don't have application, just keen interest in the fact. And let me show you. Well, I'll show you the second proof. The second proof I thought was really nice. It came from a guy who works in combinatorics, and people in combinatorics have a different mind from other people. Like probability, which is a third, like, kind of special way of thinking. So he started with this obvious identity. We know that A commutes with the powers, so let's just write that down. There's the matrix A, tridiagonal. Here's the nth power, whatever. And what is it we want to prove? We want to prove that that ratio B1 over C1 is the same as this ratio capital B1 over C1 in A to the nth. So there's A to the nth, and we want to show that those ratios are the same. So we just use this identity, multiply that one by that one, and we look only in the 1, 1 position. It couldn't be nicer. So row 1 against column 1 gives this number in the 1, 1 entry. And now if I do them in the opposite order, put this matrix in front of this, before this matrix, and do the multiplication, and just compare the 1, 1 positions, I get, well, where did it go? Did I do something that, anyway, I get this. That's the 1, 1 position from A times A to the nth, and the 1, 1 position from A to the nth times A is that. I cancel the common terms, and there it jumps out. Yeah, so that's a proof that I think couldn't be better, couldn't be improved, but it's not maybe the first one that you would think of to make that go. So that's another fact about tridiagonal matrices. So the first business about their inverses, that I think is a sort of serious part of mathematics. This is maybe more of a recreational part of mathematics. It's really nice, don't you think, that mathematics has these different lives? It's central to finite element method, for example, or to all kinds of computational science and engineering problems. And at the same time, it has these friendly nice little pieces of attractive theorems. Okay, so that's two of my main topics, and I have one more, if you're okay to go a little longer with these matrices. The next and more very much applied topic is signal processing. So we spoke about finite elements, and but now we're maybe more connecting to wavelets. So I don't know if you've met wavelets. They're really strange functions, unexpected functions. But the key property is that they are, well, in many problems are orthogonal. So we have a family of orthogonal functions of a different character than, we all know Fourier, Bessel, Legendre, and the long list of special functions. And here is special functions of a different type. And they turned out to be highly valuable in signal processing. So I want to first say what's the main topic? Where do they fit into signal processing? So can I, if there are professionals in signal processing, I hope you forgive this attempt to put the whole subject on one line. That's not right, is it? Well, you could say I'm putting the whole subject except the hard part on one line. So here's that line. That's the idea of signal processing. You have an input signal, a long vector, typically, a long vector. Every pixel, the grayscale of every pixel in an image, the volume of every little piece of a symphony. A long, long, long signal, X. Coming from video, audio, straightforward image. And you want to compress that. So we want to end up with a compressed signal X hat that has the same, has all the good information in X, but is much shorter, many zero components, many zero components. So here's one way to approach that problem is to introduce a good transform. So everything now is going to be from a good choice of this matrix A. This A is the analysis matrix. It's the matrix that takes your signal X. It could be the Fourier matrix. This could be, and often is, the Fourier transform. Take your vector X in sort of pixel space, and take its Fourier transform or its wavelet transform or other transforms, and you get a vector Y. So no compression at this point, no loss of information. This is a square matrix, invertible. We can recover we can recover X from Y. But we hope that the information is present in a better form, in a form where only a small number of components are important, right? If in the original signal, if it was the pixel values, the grayscale of pixels on an image, if I throw away 90% of X, I would have a picture that was black, 90% black. But if I take the Fourier transform and I keep only the low 10% of the frequencies and throw away 90%, I have a pretty good approximation. So this Y is my same signal in transform space. And now in transform space, that's where I can throw away 90% of Y to get Y hat. So that's the compression. That's the nonlinear step where we lose information from Y to Y hat. I'm trying to describe really a big picture, the overview of this, of what it is we're doing. And so that's a nonlinear, highly developed engineering step. Quantization goes into there, and that's not the part I think that step is done. And then from that, we recover x hat by inverting, so what's that? That's the synthesis step. Here was the analysis step, and now the synthesis step. Do you see the logic there? And again, if you already know about signal processing, forgive that simple description. But what's the goal? So if we have high-definition TV, for example, high-definition TV has a long signal that you cannot send, you don't have time to send the whole signal. So there must be compression in high-definition TV. And so you must choose a matrix A. And you could choose a Fourier matrix. This could be the Fourier transform. And that does have because you want so you want a transform with a fast inverse, because you have to do it fast both ways. And you also want it to keep the important information. And Fourier does that thanks to the FFT. But it's not perfect. Fourier will always be the best, better than any one other. If you for a one-on-one head-to-head competition, Fourier will win, except if you have signals of a certain class. And this is a big subject in signal processing, to understand, to give good description of a class of natural signals. Because, X right here is coming from, 1,000-dimensional, R1000, 1,000-dimensional space. But the natural images form a very, a not well understood, but definitely a small subset of 1,000 or million-dimensional space. So the question is how to preserve the information that's in that natural image. Okay, so here's so one way, so one way to make for a fast transform is a banded matrix. So if A is a banded matrix, then multiplication by A is fast, right? If A has only the small number of non-zeros in every row, if it's near the diagonal, then we can multiply fast by that matrix. But here I'm looking also for A inverse to be fast. So I'm looking for matrices with this property. A matrix that's banded, and also its inverse is banded. And if we think about it, not so many matrices have that property. We can think of banded matrices easily, but can we think of, usually their inverse is full. If I took my favorite matrix, the one on the first slide, the 2s and -1s, that inverse is certainly a full matrix. It's the difference between derivative and integral. The derivative is a local operation. Its inverse, the integral, is a global operation. And that's typical in solving differential equations. The matrix that gives the differential equation is local, banded. The matrix that gives the solution, the Green's function, the integral equation, is full. And there's a lot of activity now in dealing with that inverse matrix, in going directly with the Green's function. A lot of activity in numerical linear algebra is how to work with the inverse of with the integral equation instead of the differential equation. Okay, but I want to ask just an algebra question. how could we describe all matrices? So here's the question. How to describe all matrices banded with banded inverses? Yeah. It was great to see Professor Dahman before the talk today. So he's contributed to this topic and others. And I mentioned wavelets because it's the key property of wavelets. The key property of wavelets is that in the finite dimensional case, they would be called, what's the finite dimensional equivalent? So wavelets are usually for continuous functions, and filters, banks of filters, filter banks are the discrete problem. So the whole point of wavelets, the whole point of the matrix A in wavelets is that it has this wonderful property, banded matrix with banded inverse. And I want to ask, how could we describe a bigger class of matrices? So the first ones we met came from wavelets. The second, this Cmv matrix, that's a family of matrices, banded of course, that have banded inverses, that made quite a big impression in physics. So the Cmv, those are the initials of the Spanish authors of the paper, Cantero, Velasquez, what is M? I'm sorry, M is lost to history. Just Cantero, I do know. Anyway, it'll come to me. So that's a family of matrices with special properties. And then, but then we want to ask all of them. What matrices have, well, let me ask you that question. Tell me a matrix banded where the inverse is also banded. Maybe let's start with, so can you, at the beginning you might say there aren't any, doesn't happen. But then we can certainly find simple ones. So what would be a simple way to construct a matrix that's banded and its inverse is banded? Just make it diagonal, just a diagonal matrix. Its inverse is diagonal, no problem. But of course that won't get us the kind of transform that we are looking for. Okay, so now take the next step. How to get a matrix that's banded with its inverse banded. Starting with the idea of diagonal, we could move to block diagonal. If the matrix has block, 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 block down the diagonal, then the inverse will have block, 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 block of the inverse matrices down the diagonal. So that's a simple construction. But again, well, actually, in some way, that's the JPEG. JPEG uses block, 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 and that's its problem. The old JPEG images were very blocky. You could see where one block stopped and the next block started, and you see that still printed in newspapers sometimes. And then, of course, the signal processing people found a way to smooth the boundaries between blocks, but it wasn't like perfect. So, and here's a way. Now we've got block diagonal matrices, but now so now I'm going to take the next big step. So the steps were diagonal, block diagonal, because the inverse is just block, block, block. And now if I multiply together one block diagonal times another one, I think I still have a matrix. The inverse is good, right? Now, can you see that point? Okay, imagine I'm multiplying. So I have two matrices that are block diagonal, call them B and D. Now I take B times D. So what's the inverse of B times D? It's D inverse times B inverse. So again, it's block diagonal times block diagonal. So that's a way to do it. A product of two block diagonal matrices. But there's a problem there. I mean, did we get anything new? If I had a block diagonal times a block diagonal, maybe I'm just multiplying block by block, and no progress. Well, so here's the key idea. Because the theorem I wanted not to prove, but to end with, is every matrix with this in our class, every banded matrix with banded inverse factors into a B times a D, a block diagonal times a block diagonal. Block diagonal times block diagonal gives everything. And therefore, we have a class of matrices to optimize over, to choose out of that class the best or good matrices A for signal processing, and wavelets, of course, are good examples, but other examples are constructed. So that's the theorem, but I have to say again, if I'm just multiplying up one block by another block, I'm not getting anything new. I would still be just block, block, block. So what's the key idea? Let me see it. Oh, okay. Well, so this is I just thought I should show, well, there's a, oh, heck with it. Yeah. Let me come to the, so this is our problem. There's my favorite matrix. The inverse of the favorite matrix is full. That matrix is full. It should have many more dots because, so a matrix like this can never have the property that we want. Those simple filters, that matrix comes from a simple averaging filter. That could not have the property, or maybe that's a high pass. Yeah, that's a high pass filter. The inverse of that matrix will be full, no good. So let me continue to the, here's the key idea. Here's the key idea. So this is a block diagonal, 2 by 2 blocks. You see, I'm calling the matrices now F and G. Okay, so 2 by 2 block, 2 by 2 block. So the inverse of F it looks just like F, has the same structure with the inverse of this block, the inverse of this block, and onwards. Now here's G. It's 2 by 2 block, 2 by 2 block, 2 by 2 block. And again, its inverse is 2 by 2, 2 by 2, 2 by 2. But do you see the key point here that makes everything work? The key point is that the G matrix, the blocks here, the block in the G matrix is offset. It's halfway between those blocks. So, and that gives the complete description of our class of matrices. So a block diagonal matrix times an offset block diagonal matrix. The blocks are in different positions, and then when you multiply them together, it spreads out, and actually you get everything. Yeah, so that's the theorem, and I will not give a proof for that, but it describes then wavelets that we knew, the Cmv matrices that we knew, and a much larger family of filters. Time-varying filters are now included because these can be different as we go forward in time. So we have the possibility to create time-varying wavelets that are good when the signal characteristics are time-varying. Okay, that might be, so that's my final, there's the proof. No way to do that. Go, leave, get back. Okay, so maybe I could stop there with the three, may I just sort of remember the three topics? Well, let's see, I have to remember. First was tridiagonal matrices and completion and inverse. So in completing and inverting. The second was that curiosity about the ratio of off-diagonal. And the third is this description of matrices that are banded with banded inverse. So it's a lot of linear algebra you've been asked to hear today. I hope that's okay. It's well, it's just a beautiful subject. And I'm happy to see that in the curriculum, in engineering curriculum, in mathematics curriculum, linear algebra has moved beyond, it was originally, or 50 years ago or so, it was just it was small Hilbert spaces for mathematics, people doing mathematics only. But, and engineering would be always differential equations. But now those two, the continuous and the discrete, the two big parts of mathematics are coming in parallel. Differential equations for the continuous problem, matrix equations for, so linear algebra, for the discrete problem that you actually compute. And the connections between them is what numerical analysis is, much of numerical analysis is about. So thank you again for inviting me here. Thank you.